Good morning, everybody, and welcome to the intersection of the Clay Research Conference and the opening conference for the new mathematics building, the Andrew Wild building. We're delighted to have with us Ingrid Daubechies to speak, to join these two events together. I hardly need to introduce one of the leaders of our mathematical community, because everybody knows about Ingrid anyway, but just to say that she's had a stellar career which took her from Belgium to the Courant Institute, Princeton, and now to Duke, president of the IMU, won numerous prizes and awards, and of course in at the foundation's inventor of the Daubechies wavelet, and without wavelets we wouldn't be sitting here watching the nice projections we're about to see. So, ladies and gentlemen, please welcome Ingrid Daubechies.
Okay, so, well, this is the playful title for this talk. I mean, it also has a more serious title, which actually already has a conundrum in this. Distances between surfaces. This is a project I started working on about 5 years ago, and I learned then that there was a discrete differential geometry, which seemed to be an absolute misnomer. I mean, how can you have differential geometry for discrete? But it's actually a very interesting subject, and I'll come back to that misnomer. Most of it is, well, all of it is joint work with many people, but the person with whom I've worked most on this is Jeroen Lipman, who, when this picture was taken, was a postdoc at Princeton. That little baby is now this toddler. He is now an assistant professor at the Weizmann Institute. He is a mathematician who is an expert in computer graphics. Computer graphics is the field that it's a very big field. It's a field that drives, that does the theory and develops the algorithms for video games and computer animation like Pixar movies and so on. And what I very much like about Iran is that all computer graphics algorithms are very clever, and but many of them are very ad hoc. And he likes to base his understanding of differential geometry, which I believe, as a mathematician, is really the right way. And so, when he came to be a postdoc at Princeton, I thought that was a dream opportunity to start a topic that would use all of this beautiful algorithmic approach for an application to the sciences rather than to animation. And Jeroen was delighted with that, and that's what I'm going to talk about. But let me first tell you about animation and why I thought that some of the tools developed in computer animation could be useful for the biological applications I'm going to discuss later. So, animation uses computer graphics, as I said, and computer graphics relies on three-dimensional mesh models. So all these Pixar beings that you see in these movies like Toy Story and Monsters Inc. and so on are really 3D mesh models on which texture is projected, and so they're surfaces that are animated. And nowadays they have further things like flows of liquids and hair and so on, but in essence it's 3D surfaces. And the very first one of these lifelike objects was the teapot. The teapot started because in the late 70s or maybe early 80s, a friend of one of the computer animators who was talking about these surfaces and so on, he said, why don't you just take an object? And she held up a Melita teapot. And so this was the first meshing of a teapot. And the teapot, in the meantime, has become much more sophisticated. It looks more recently, with thousands of little facets and nicely rendered instead of the very crude one you saw earlier. A little insider secret, if you go to a Pixar movie, any Pixar movie, somewhere in there is a teapot. I mean, it's an inside joke of computer graphics is that they always put a teapot in there. I mean, it can be as part of a toy set or okay, so as I said, 3D meshes became much more sophisticated over the years. And here are images that I borrowed from internet. This is a make-believe architecture application. This is actually a design of a manufacturing of a part of an engine. Here, these are characters of Toy Story movies. On the left, you have Woody from Toy Story, the Toy Story series. And Woody, as originally all Pixar characters was made out of a triangulated surface, well, quadrilateral surface, but what it was a surface that was, they were nerve surfaces, so piecewise splines that were knitted together and with seams with the right boundary conditions in order to make the full character. And it turns out that when you do that, it's really a big pain to animate because these seams and so on have to animate as well, and you can do that. But then they start doing things with the surfaces that are not exactly what you like. And Pixar changed over. For Toy Story 2 was the first well, actually for Bug's Life and then Toy Story 2 as well, to a different scheme which is called subdivision algorithms, in which they, instead of starting by taking splines, which we like very much from approximation theory, they said, well, we want to have something where we have local information and then fill it in order to get smooth surfaces. But let's try to take that literally, instead of saying, these points are coming from a spline and so on. And when you do that, you see, if you want a smooth spline, and I say I want it to go through these points, just think of a one-dimensional spline. You want it to be 1 here and zeros elsewhere. Then, so you want it to be 1 in one point and zeros elsewhere. Then what happens is that you get a function that does that. But in between, it oscillates. I mean, this thing will have an exponential decay, but it will stretch to infinity. If instead of that, you say, I have points that I want to have this kind of behavior, 1 and zeros elsewhere, and you could, and this is a rule that's perfectly acceptable, and it's done in 1D, you could say, at this midpoint, I want to invent a new point, and how shall I invent it? Well, I'll invent it so that if I try to make a cubic that went through these 4 points, then I would look at the function value there. And it turns out that it's very easy, a very simple calculation gives you that you take 9/16 of its 2 neighbors, and you correct by subtracting 1/16 of the value elsewhere, and that gives you just something a little bit above the midpoint. And you do that everywhere else, and then you keep doing that. I mean, here, after I've defined all the midpoints here, I'll look at 9/16 of its neighbors and minus 1/16 of, and so on. And if you do that, you build a smooth function that also oscillates, but that stops here. It's absolutely contained within an interval on both sides. So it doesn't have this exponential decay. And it's a very nice, it's called subdivision. You define a function by refining it. And subdivision is what's used now in computer animation. The figure on the right, Jerry, was the first character that was made with subdivision graphics. So one hand of Jerry with all its fingers, all of which would have had seams and so on, and its fingernails, which would have been a separate nerve when they did with nerves, is now one surface. And all these different branchings are controlled very easily. And it's much easier to animate. And so it's interesting mathematics that is actually related to weight loss. I mean, that's the closest to complicated in this talk, used for these figures. But all that is for creating objects that you then want to animate. For applications to biology, I'll be interested in doing things with existing objects. So if you have an existing object, then you can acquire, you can learn of its geometry by first scanning it. Here that's done with a laser, and you can do, for instance, time of flight for the reflection. That will give you geometry information. Or you can project different kind of barcodes on the 3D geometry and photograph it from many different angles. And that and the distortion of that will teach you about the geometry, and you can reconstruct from that. Now, what you reconstruct from that is first a point cloud. I mean, you have points in 3D that correspond to a noisy version of your surface. And there exist algorithms for denoising that and for triangulating that. And I won't go into those, because that's a separate thing. Here's an example of, again, stolen from the internet, borrowed, of an object that was scanned. Then on the computer screen, you see the virtual rendering of the surface, the triangulated surface that was made from it. And that was then used to make the object on the right, which in this case was milled. I mean, right now we would do a 3D printing for something like that. We can't, with these digital models, make these objects. You can use, of course, once you have a nice triangulated surface, you can use it for all kinds of things. And here I have on top a subdivided surface that has, as this camel hat, you see the subdivision, the triangulated surface on top, you see the rendered head below it, and then by moving some of the control points at a coarse scale and filling in the fine scale again, you get your camel to top. I mean, but that is not what we're interested in here. What we're interested in is taking existing objects and scanning those and doing things with it. Well, you can see that if you have twice the same object and you scan it twice, it's not immediately obvious that you will recognize it as being twice the same object. The point cloud will be different, your surface will be different. How are you going to recognize it's the same thing? Or, and that's that it's very similar thing, not quite the same thing, but very similar. Or how would you quantify the difference between two objects? Here I'm showing a Volkswagen Beetle and a dinky toy version of it. So in fact, one is not just a scaled version of the other. When people started making dinky toys, they found that if they just scaled them down, they didn't look right. They looked too long. So they had to make them a little bit stubbier to get the Beetle feeling at the toy stage rather than the big one. And so, I mean, you might hope if you did scanning of surfaces and so on to be able to quantify that. But it's not obvious how to do that. And another problem about recognizing objects and identifying special features of them is something we come across in animation as well. It's when they have humanoid characters, they actually first have actors go through motion, and they do what they call motion capture. What that means is that they put special emitters on crucial joints and reference points on the actor and film the actor while moving. And they then have the motion of these special reference points, and they look at the humanoid character where they have the same reference points, and those then control that motion. Now, to make animated movies or video games, there's tons of money. I mean, but one application that people like to do is try to do study motion of animals. For instance, at Duke University, there's a lemur center. Lemurs, it's now illegal to export any lemur from Madagascar because they're endangered. But a long time ago, when they were less endangered, this was not the case. And Duke actually has the largest lemur center outside of Madagascar in the world, and they actually have a vast, expansive forest in which they live and have adapted. And but many scientists are interested in working with these lemurs for different experiments. For instance, cognition experiments in primates. It's great. I mean, lemurs can count until 6. I mean, I saw one experiment. It's very obvious that they can distinguish 1, 2, 3, 4, 5, 6, many. And actually, they like doing these experiments. I mean, they're primates. They're curious. So, in order to get the lemurs to participate in these experiments, they have taught them a few, because they like to keep them as wild as possible. Of course, they don't want to tame them, but they've taught them a few hand signals so that they have learned that if they obey those hand signals, they will get into a little transporting cage, and then they go to a lab and they get to do all these fun things where they get treats if they recognize that they were 4 and not 5 objects. And so they like doing that. But the motion, I mean, they're also interested in checking how much energy lemurs spend while in different ways, in different gaits, in different ways of locomotion. And, to see, for instance, whether in the wild they can judge from how they move, whether they are feeling the predation of their environment or not, and so on. So there's a whole lot of questions that biologists study, and for which it is very useful to be able, under much more controlled circumstances than in the wild, to observe the gaits of the lemurs. Now, to do that, they need to capture their motion. And to capture their motion, they have to attach little tags to these lemurs, and since they have this hair, all this fur, they have to shave a tiny little bit and then attach something, and lemurs hate that, so as you might expect. And so they would be very interested in ways of capturing motion, just like that would not involve this. Now, this is, as I said, it's a question that people have been interested in for animation. And that's one way in which biology could benefit from all this money that goes into animation, because no way could biologists, or even if they could, they would not invest in that, afford all the money needed to develop that kind of software. But animation can, and once it's developed there, it can be used. So that was what where that was one way in which things that get developed for computer animation can be used to do interesting science then. So to summarize, we'd like to be able to recognize when 2 point clouds correspond to the same surface or to very similar surfaces. We'd like to quantify when 2 surfaces are different, how different or how similar they are to each other. And if we have 2 surfaces that are very similar, we'd like to find a mapping that will take one to the other. Now, the application I was interested in is an application in biology to what's called for morphologists. So these are people who like to study whole animals or parts of whole animals. So biology has made enormous strides in molecular biology, but and that's fantastic. And it's to the point that when my children were doing biology in high school, it was not at all the same thing anymore, even in high school, as what I had learned in high school. I mean, there was so much transport mechanisms in cells and so on, and we had learned about the ant and the frog. One consequence, I mean, if you then go to the genomics level, and biologists want to understand and study evolution. If you go to the genomics level, which is where a lot of evolution studies now concentrate, people who do morphology, and it's a little bit an exaggeration, but there's a ground of truth in it. They say, well, a lot of progress in genomics has happened, but partly because once you get to the bottom of it, and let's not downplay all the difficulties in the mathematics of that, but the basic principle is that once you've unraveled it, you have something linear with an alphabet of 4 letters. Now, it's true there can be all kinds of faults and mistakes and interspersal and so on. So you need good algorithms to do that. Still, the bottom line of it is that it's a much easier thing to define distances between two strands of that nature than between two surfaces. I mean, surfaces in 3D with all their bumps and so on, to find that, to look at similarities there is a much harder thing. And so this happened all because I met at a social event a biologist, a morphologist, who was telling me that that in his field, what they were doing in order to compare surfaces was that graduate students or postdocs would look at a collection of things they would want to compare, would study them, would use their enormous knowledge of what they know about biological correspondences to find features that were in common between all these teeth, and would then painstakingly, on digitized models, it's not that they had stayed in the prehistory, I mean, they were looking at very finely discretized models of these teeth, which incidentally they make by using very fine dental resin and making casts of the teeth and then analyzing, which they can do in museums that would not lend them all their beautiful specimens, but they can get those and then take those casts back and analyze those. Anyway, they have these very high resolution models, and they look at corresponding point, they tag them kind of manually on their computer screens, and then they have for each of these tooth about 20 correspondence points, and then they start using distances between these 20 tuples of points in R3. And typically they try to move them in the most closest possible R3 correspondence, and then they add all the Euclidean distances squared, and that gives them what they call the progressive distance between these teeth. So they have a proxy, but they have to do this manually, and it's only possible if they really understand these biological surfaces very well. And so it takes 2 to 3 years for a graduate student or postdoc to be sufficiently trained to do this reliably. And the result is that it's a field that is much less open to others than comparison of genomes is, for instance. And they felt that this was had really hindered some of the usefulness of these methods. Also, they have the reputation, although they're not quite as subjective as some of their detractors say, they have some subjectivity in it because it depends on the training of these individuals. And as a result, so this morphology quantifying has not had as much impact on studies of evolution. And in the end, you really do want to have a good way of assessing differences between organisms, because the genome and the genetics is how evolution works. It's the mechanism by means of which traits get transmitted. Well, we're now learning a lot about epigenetics, but let's leave that aside for the moment. But the way the environment interacts with the organism is not straight on the genome. It's via the shape and the organism itself. So if you really want to understand, you need to have both aspects of it. And anyway, so that's how I was motivated in order to. And so when Yaron came as a postdoc to Princeton, I said, well, all these things you do and you know for computer graphics, for the SIGGRAPH and the animation industry, maybe we can use this. And so, of course, the first thing he said, everybody says, is, come on, people must have tried to look at differences between surfaces. And surely, indeed, there are many. But most ways that people try to compare surfaces do in fact rely on such tag points. I mean, you can mathematically say, I'm looking at critical points on the surface or so on. In fact, the biologists, that's first also what I thought that the biologists did. The biologists do like things that are critical points, but they also look for other points, which I was very surprised. We still, I mean, and of course they learn this by osmosis. They don't really articulate what they do. I mean, so we don't actually quite know exactly yet what they do. But there have been proposals to use other things than tag points. So one of the first ones was Gromov-Hausdorff distance between surfaces that can be quite similar. I mean like a giraffe and a pig or so. But they are very heavy to compute. And in fact, when we tried to apply them to these teeth, because the morphologist with whom I was talking was especially interested in comparing teeth of mammals, molars of mammals, it turned out to not give such very good correspondences. So the things without tag points were not satisfactory. So we wanted to develop an approach that was different, that also would be much faster computational, and we wanted to be inspired to some extent by what the biologists did. And so we talked with them, but mathematically. And so we have a number of different approaches. I'll sketch one of them in a bit more detail. We have still others. But in all of them, we try to do mathematically something that corresponds somewhat to the intuition of the biologist. So when we observe the biologists, it's very clear that they look at local features. So, for instance, minima, maxima, critical points, and so on, but also other things. But they look at local features, but then they also look at how these local features fit together in the global thing. So we felt we needed something that had both local and global aspects in it. And that was one of the driving mechanisms for what I'm going to describe now. So we also, in order to, the teeth, the molar, so we look at molar teeth, and we are interested only in the chewing surface, so the top surface. So our surfaces are things with lots of bumps, and we stop at some point where they go down and so on. They're no longer functional for chewing, so we stop scanning the surface at that point. So we really have disc-like surfaces, so we can uniformize them to the disc. And so we did that, so we reduced them to flat discs in order to have faster algorithms. Okay, so let me explain a little bit for those of you. For me, it was when I first started this, and I had to get back to the differential geometry. It was over a quarter century ago that I last used differential geometry. So, and maybe some among you who are in the same situation. So okay, so we have a 2D surface in 3D. It, of course, inherits a metric from 3D, so you can measure distances over the surface, closest distances between points. It is a Riemann surface with that geometry, and what that means is that you can, in fact, define angles between tangent lines to the surface. You can define orthogonal lines, and in fact, you can use that, the fact that you have a nice, consistent way of defining orthogonal lines, orthogonal curves, to map the whole thing in conformally to a disk. What that means is that any curve gets mapped to a curve, so that when two curves intersect, they will intersect with the same angle after you have flattened it. And we have to do all this computationally. I mean, we're going to have to discretize the whole surface, and we'll have to work with this computationally. And it used to be that when you wanted to compute things, some nice continuous structure, you would try to make a very high order approximation to it that was discrete via high order splines or something like that. And then, because it was a high order approximation, you now had a discrete version of it that had a lot of the original in it. And we have moved a little bit away from these high order approximations. I mean, instead, it turns out, for this and many other applications, that it's much better to try to understand the full mathematics of what you're doing. In this case, the conformal mapping, the uniformization map, the keeping of this orthogonality, this complex structure that you could define on the surface, and then build a discrete analog of that, and use that in order to do your approximation. So you construct an approximation that is discrete and that has the same marrow, if you want, the same essence in it. And we see that all over in applied mathematics. You see it in symplectic integrators, you see it and so on. when you want to compute, it's good to have really understood the mathematical structure and take that in order to build your approximation, rather than to be high order and only approximate having the right structure, because then you lose it as you do more steps. So that's the whole conundrum of discrete differential geometry. You take the differential geometry, you see what the important things are, and then you build a discrete structure that has those right properties. Okay, so how do you in fact do that? So I'd like to explain a little bit about that. So a conformal mapping means that you preserve angles. We started with our surface and it's triangulated. You want to flatten it. Preserving angles mean that for every one of these triangles, I can scale it larger or smaller, but I have to map it to a triangle that is similar to the original triangle, since I'm preserving its three angles. So it's very easy to see that if I want to keep this whole mesh with all these triangles that have sides in common, and I want to scale the different triangles, but I want to keep the mesh structure intact, the only thing I can do is blow it up or scale it globally down or up. I want to flatten it. So the first thing I can do, this is one way of doing it, but there exist others, is to actually encode discretely the geometry in a slightly different structure. And this can be done via what's called the mid-edge point triangle mesh. So what you do is for every one of those triangles, you take the three midpoints of the sides and you make that little internal triangle. That is already a triangle similar to the original triangle, really, obviously so. And you do that for all of them, and so that gives you a whole midpoint triangle mesh. And it encodes the full structure of the original mesh, because two triangles have a vertex in common in this green thing, if the original ones have a side in common. And I all have these similar triangles. I have all the angles there. And so that lacy kind of thing is something, to me, it's exactly like a crochet lacing thing that's trying to follow the surface. That, by stretching and so on, and ironing a little bit, you can flatten very nicely. And so when you do that, you have done a conformal mapping. You have kept all the triangles in their shape. Now, you have now a mid-edge triangle mesh that is flattened. If you were to try to make the big triangles out of it again, you would see that the big triangles wouldn't have, they wouldn't fit anymore very nicely in a mesh that lines up exactly. But you have encoded geometry and kept angles and so on. And you can prove that if you take your triangulation to finer and finer, you get closer and closer by this mapping to the continuous conformal mapping. So you do the right thing, even though you don't have a high order approximation at all. Okay, so this is what happens to a piece of my tooth surface, and here you have mid-edge triangle mesh. This is what on the left the tooth and the mid-edge triangle mesh. Now this is a tooth of a mouse lemur, a leopard lemur, which is an animal this big. So you can imagine its second molar on the bottom left is kind of a bit blown up. Now, an interesting, fun thing. So you have these tooth, and I said it's disc-like. So if I did my triangle mesh and I ironed it and so on, it would become a kind of pancake shape with frilly edges. And of course we know that we can take any such shape with a nice border and map it to the disc. There exist conformal mappings to do that. Engineers and mathematicians have been doing that for ages. But of course for every frilly shape, it's a different one. If you have a different frilly shape. In order to do something that is universally valid, so that you don't have to adapt every time, Jeroen discovered a very interesting fact. If you don't try to iron the whole thing down, but instead you take out one little triangle, central triangle, and you map that over infinity. So what we have done here is that these, this and this dot are really the orphan vertices of a triangle that starts here, then goes all the way back and ends up here, over infinity. Now, Fine. But I had a rim to my surface. That also gives me little orphan vertices in my mid-edge triangle. All those vertices end up, because we did a construction that has exactly a nice complex structure, and we didn't try to approximate it, but we discretely built it the right way, they end up on a line segment, discretely. And so the result is that since we all know we can all construct if we're given 5 minutes in the privacy of our offices, the conformal mapping that maps the slit disk, complex disk, or which interval between 0 and 1 is removed, to the slit plane to the disk. So you have one conformal mapping of all of these different surfaces to the disk. You don't have to adapt every time. So that's one benefit of doing discretely the right geometry in order to work with this. But that's just a little side note. Okay, so let's do that. And here, this was done for model. One of the models. Computer scientists have gone way beyond the teapot. They now have the bunny, the David of Michelangelo, and this is the cat. So here are two positions of the cat in different positions. And what this is illustrating is that after I do this whole reduction to the disk, they actually, even though the surfaces are not the same, since things have been stretched and deformed, we recognize the same structure. You see, the head and legs are all here, and the two hind legs and the point of the tail. And you see that these are not the same triangulations. Look here, things do not quite look the same. But you recognize, nevertheless, in the whole construction, similar things. Of course, I have swept something under the rug here, because I'm talking about conformal mappings. And once you're on the disk, you can still conformally map the disk into itself. In fact, you can map any point to any point, and then any one point to any one other point conformally. So you still have a 3-parameter group that is conformal for the whole disk. So if you start with even two identical surfaces, let alone two surfaces that are not quite identical, you're never going to end up with exactly the same. And in fact, this is typically what you would get. So what you have to do is you have to compare not the two discretizations you get, but one discretization with conformal versions of the other. And so if I have the one here on the left, and I then look among its other versions, I will find one that is very similar. Okay, so, and that's what we're going to exploit. How are we going to look at the similarity? When you do this flattening, you have enlarged some triangles, shrunk some triangles, and so on. So you can look on your disk and you can actually keep track of how much you shrank and enlarged different triangles in order to do the ironing and to flatten it all. So that's called a conformal factor. So you can make a landscape on your disk of this conformal factor. Where did I stretch a lot? Where did I not? And so on. And that gives you can imagine it as a landscape in sand. And for the two surfaces, after I have looked at the conformal, I've looked at one version, and I've looked at the conformal version of the other one that looks as much like this as possible, then I can try to see how much do I have to move sand around in order to get to the first one. And that basically is what we're doing in trying to define a distance. And I could go through these different formulas, but let me not do that because I will go over time otherwise. So in the end, what we do discretely is we approximate these conformal factors on the disk for each of the two. We define a way of doing mass transport from one to the other. This sand heap landscape moving its optimal transport, mass transport, and we do that in a conformally invariant way. So in fact what we do is we look at neighborhoods of different points in each of it, and we look at the conformal way of moving this one so that it's most similar to that one, and then in that most similar way we see how similar they are. And so that gives us a distance, and we can then move that, a similarity distance, and we can then use that in an optimal transport. And so you see we were looking at local similarities, and then we were trying to knit it back together in a global transport thing. So in that sense we were doing something locally and globally, like the biologists were doing. Okay, what's the result? And also optimal mass transport, there has been a lot of work in trying to make that efficient computationally. It can be done via a linear program, so we can actually work with it. We have other versions of distances, and we actually are still working on others. We are now looking at quasi-conformal maps. We're looking at area preserving or optimal transport with some loss of mass and so on. And I can talk about that offline if you want. Let's look at what it gives us. So before before we actually had results, we had agreed with the biologists. I mean, how were they going to evaluate how good our stuff was? Because we could define norms and so on and say it's very close in that, but the proof of the pudding wasn't how useful was it going to be for them. I mean, so one thing we had decided we would do is that we would compare if they had two teeth, for instance, and they put similar points on the two teeth, then if we were given those surfaces, we would define a mapping that we would define as the best corresponding mapping between the two teeth. So we could then take the points that they designated on one, use our mapping to transport it to the other one, and we could compare what we found with our transport with what they would have put as points. This is shown here. So at the top you see the tooth, and here we look at teeth that are very different. And a primate tooth, molars, and this is how we propagate those. This is how they would have put the molars. And you see, we're not that far off. I mean, the reviewer of that paper wanted us to also look at other things than just teeth. I mean, even though this is already, a stretch. These teeth are very, very different. But we looked at radii, the end of a radius bone in human and ape, and we looked at a metatarsal, which is one of the foot bones in different types of primates. And in all cases, we found pretty reasonable maps. Another way in which we had agreed ahead of time to compare was that we would really look at the distances that they computed with their proboscis way and our way of doing it. And these are color diagrams from matrices to show that comparison. So the ODLP is the observer-determined landmark placement distance. We are looking here at the distance I described with the neighborhoods and optimal mass transport, which we call the continuous neighborhood distance, and here continuous proboscis distance, which is another one which I haven't described. And we had ordered the different samples in such a way that labels that were very close to each other were more similar, according to the biologist. So what's especially interesting is things near the diagonal, because those are things where we are very similar. And so you see here, especially for this other distance, which I described less, you see that we are very, very similar. There's the structure near the diagonal of these two distances. I mean, blue means very similar, and then you go through the rainbow, and red means very distant, are quite similar. Here they're a little less so. We have since understood that that's because the distance that I described to you where the flattening and the conformal factor only uses intrinsic geometry, and we do need a little bit of extrinsic geometry as well. So we're now using that, and the continuous progressive distance does that. Now, why is it so interesting that you have, especially when this is so close? We have now, and this is not something that is just peculiar to us. We do know that when you try to learn data that have very complex structure, but that live on a low-dimensional manifold, that when they're very similar, you can get a pretty good reading of how similar they are by using very coarse methods, Euclidean methods. And because, well, you're very close to the tension plane. And then if you have pretty good readings for all these small distances, then even though these are pretty coarse readings for each of them, they're coarse type of approximations, but they happen to be good because you're so close. Nevertheless, the whole mass of them has enough structure that you can knit the manifold back again from the whole thing by using, for instance, diffusion. If you diffuse by little diffusion distances and you map those diffusion matrices together, you get a diffusion operator over longer distances. So, and indeed, we are working with that now, and I'll come back to that in a sec. Then, one thing they had asked us to look at was an application that already incorporates this idea of smaller hops are more to be trusted than big hops. So here we are comparing a microcebus and a lemur, and this particular point was a controversial one. So this is a correspondence like if people took those two teeth in a set, then they would try to put this in correspondence with that, and it seems entirely reasonable to do so. But in fact, they would be wrong. This is controversial, but they would be confusing this, which is an entoconate, and they believe that's a metastylet. Now, apart from those two names, you have now uncovered the full extent of my knowledge. But what they asked us to do was to say, look, instead of this comparison, you were to do smaller hops. And the path that they proposed was one path, a smaller hop, and then back to this tooth, via a common ancestor of both the species, an extinct ancestor from the fossil record, or via two extant, two still existing species, but that are more closely related to each other, and so three hops instead of this one big hop. And in both these cases, you find that this yellow dot corresponds to this point, and here as well, rather than to that metastylet. So they felt that this was showing that our geometric method was behaving like what biologists would find themselves in their observations, which is something they wanted to see our automatic method do. So where are we? As I said, we have made a bit more progress since then. These slides are now 2.5 years old. We're still refining the way of making distances between our teeth. We have learned that we really should work with small distances, and from small distances map things together. But by the comparison that I was showing earlier between a non-primate and a primate tooth, this distance is still a very small distance. So this should not be an illegal comparison. What this is showing us is, if you think about it, we believe that these teeth, their surfaces, so they're high-dimensional things, many degrees of freedom in order to manufacture a surface, like these teeth. All these different teeth, and they have, if you talk to a biologist about teeth and that you can do something with our computation, they pull open drawers and there are hundreds of them, so zillions of teeth. And we believe they are all points on a manifold. And if you don't start comparing goats with dolphins, if you stay a little closer, then you have a fairly well-populated manifold. And on this manifold, we have learned to look at distances, and so we can find the geometry of this manifold, and we hope, for instance, to get some idea of the dimensionality of that manifold, and we ultimately hope to connect back to what influences the growth of teeth and genetic factors and so on. People have good understanding of morphogenesis for teeth. I mean, they start to have good understanding, and so we'd like to connect back to that. But, so we have this manifold. But we don't really have just a manifold. What we really have is a fiber bundle, because every tooth is really a complete surface. And we have mappings between the surfaces. So we have a connection. So we have a manifold with a connection on it that we're learning. And what this is telling us is that the connection is something where if you do a circle, you don't get back to the original. So you have some curvature to your connection. So we can try to compute that. And when we were explaining that to the biologists, they were really excited because to them, I mean, so that we are now interested in trying to do a coarse graining of this. I mean, there might be regions where you can make bigger circles than you can do for the whole tooth. I mean, they're interested in how stable these things are in evolution. I mean, so we're developing a framework that we hope we can compute with and will be really useful to understanding some of these biological concepts. Now, the first thing I did, of course, I mean, as I told you at the start, I mean, differential geometry for me was, my God, not even more, something like 35 years ago when I was a graduate student and looking at general relativity, not this type of differential geometry. And so I go and talk to differential geometrists, and I said, look, somebody must have looked at fiber bundles and connections and coarse graining that. I mean, I said, well, we don't really know. I don't think so. So that makes me extra excited because that means that we have here a way of looking at application that may suggest new mathematical theory that needs to be constructed. And heaven knows it might then be useful, as it so often is, for many other things in mathematics. So let me stop here.
We have time for a question or two.
Yes.
Have you looked at comparing surfaces other than teeth?
Well, for the moment, we have looked at not just disc-like. If you were asking whether we were looking at other types of surfaces, certainly we've looked at other bones. We've also looked at things, metatarsus and so on, that are sphere-like, I mean, where we took a full bone. So we can do the things for spheres and not just discs, where you don't have as natural, I mean, well, where the construction has to be changed a tiny little bit. But, and we should be able to do it also for homogeneous surfaces by looking at universal components, but we haven't done that. Yes?
Is there some sort of biological foundation for looking at conformal maps in the first instance?
Okay, so yes and no. The reason we looked at conformal mappings was that we were very interested in making the computation easier, and the conformal mappings are much easier to search than area preserving maps, for instance. But we can also prove that if two surfaces are fairly close to each other, for instance, in a continuous procrustes distance, then there has to be a conformal mapping that's very close as well. I mean, so if things are not far, and that's fairly reasonable, that if things are not far apart, then there's a way of deforming one to the other that's conformal, and that is even closer to the other. And so we can prove that, and we use that as a justification to do our search in the conformal group. And then, if we wish or not, we can, from there, find a close-by area preserving map or an almost area preserving map. So our computation, our motivation is mostly computational. On the other hand, there are definitely situations in which biology does seem to work in a conformal way. I mean, there are things in embryonical growth, for instance, where some angle preservation seems to happen, but there are others where it doesn't. So. Yes?
Have you tried anything with missing data, such as if you had half a tooth?
Now, we haven't yet, and but ultimately, so can we handle missing data? We haven't yet, and but ultimately we of course would be interested. It's not just a half a tooth. I mean, it's also an abraded tooth. I mean, sometimes you have tooth in perfect preservation, and sometimes you have tooth of animals that are a bit older and teeth are worn, and then you have to deal with that. So for the moment, we are trying to. I mean, these are real teeth, so we're not trying to just work with models, but we're trying to work with fairly good teeth. And then when we feel that we're already at the stage where we're doing as well as people who are well trained on good specimens. I mean, once they are less perfect, they know more than we do, than our algorithm does on preparing those. So we haven't really perfected that at all. But on the other hand, I mean, it takes biologists quite a while before they can deal with those as well. So we now are as good as a student who's had 2 or 3 years of training. And actually, one of the authors on the paper that compared our results with a trained biologist was a graduate student who said, well, this was absolutely wonderful, but couldn't we have done this 3 years earlier? So that she wouldn't have had to spend all that time. But it's even that is still quite controversial. I mean, there are people in morphologists and biology who hate the idea that an algorithm can do this. I mean, we thought they would all be ecstatic that now they could be spending their time on things that no algorithms could do. But it will probably take a little while. Yes. Oh, no.
Okay, well, before we thank Ingrid again,
Was there another question? Oh,
one more.
yes.
Sorry. There are also sort of topological methods to sort of compare phenotypes in the industry, but biology uses things like persistence homology to do these kind of comparisons.
Yes.
Have you looked into this as well? Are these methods, topological methods, just more coarse than these ones? They just look finer to me. Did you try them?
We haven't tried them, but I have discussed quite a bit with John Hare, who is one of the people who is a strong advocate of topological methods. And he agrees with me that what the biologists really are distinguishing here is information that is too fine geometrically. I mean, it's not just a question of the height function. It's more delicate than that. And I mean, he has a student who looked at them, and it didn't. We have other projects on which we do want to work together but they have more to do with boot systems and so on, things where branching, things where it's less fine grained in kind of geometric nature.
Okay. Before we thank Ingrid again, could I just say there will be sandwiches upstairs before we resume at 2 o'clock. But now, that was a wonderful lecture. Thank you very much.